of discussion for today is radioactivity. So radioactivity is the spontaneous emission of radiation, or we call it the spontaneous disintegration of the nucleus, resulting into the emission of radioactive particles. So we can say radioactivity is the spontaneous. Are we together? 2 seconds, please. Let me admit this person. Disintegration of the nucleus of an atom, right? Resulting into the emission of radioactive particles or rays. So this is what we call radiation. So it involves the spontaneous. The word spontaneous here means something that occurs on its own without any external factor. Okay. So when you have an entity of this size, and this entity is an atom, and the nucleus of this atom is disintegrated, leading to the splitting or the breaking down of this very atom into another smaller atom, possibly with emission of radioactive particles. Are we together? So this process is known as radiation. Are we listening, please? This is radioactivity, and sometimes we call it radioactive decay. Most importantly, when the radioactive particles involved include alpha particles, please, am I talking?
Yes, sir.
Beta particles, and then the gamma ray. Now, when you have these major particles or rays being emitted during the spontaneous emission of an atom, we call that radioactive decay. So, radioactive decay involves the disintegration of an atom, resulting into the emission of alpha, beta, or gamma ray. So the process is known as what? Radioactive decay. So when your where the emitting substances are simply alpha particles, beta particles, or gamma ray. But when you have generally the spontaneous disintegration of the nucleus to emit radiation, so this is known as radioactivity, irrespective of whatever that is being emitted. But if the particles emitted during the disintegration are alpha, beta, or gamma ray, so we say that is known as radioactive decay. Is that okay? Now, the conception of radioactivity began by a scientist whose name was Henri Becquerel. So, he's known as the father of radioactivity, right? So, the father of radioactivity is who? A French scientist by name Henri Becquerel. Are we together? So, he made this investigation in the year 1896. So, how did he get to do that? He was able to detect the effect of radioactive particles when he was in his lab, and he discovered that a photographic plate was getting faded. So when he then investigated what was the cause of the fading of that radioactive the photographic plate, then he came to realize that there was actually a substance that was making an emission of a radiation over the photographic plate, and so he later discovered that that substance was made up of uranium. So the first radioactive component that was first discovered was what? Uranium, and that was what was discovered by Becquerel in the what um, investigation on the photographic plate. Are we together? I hope I'm saying something. Hello?
Sir?
Are we getting it?
Yes, sir.
Now, years later, Henry Becquerel, after making this investigation, didn't stay long, and he actually died few years after his investigation. So, in the year that is 2 years later, that is 1898, a couple by name Pierre Curie and Marie Curie, they are also French scientists. Pierre Curie, right? And what? And Marie Curie. Are you following? These were the ones that furthered their investigation or the proposition that was made by Henry Becquerel. So they observed that a natural substance made up of the pitch blende. So the pitch blende was observed to have a lot of radioactive materials. So in the discovery of the pitch blende, they got to realize that the effect of uranium that was observed by Henry Becquerel was more intense in the pitch blende. With that, both Perry Query and Marie Curie did a lot of work, and they observed a lot of radioactive materials from this natural substance called the pitch blende. So from the pitch blende, they realized two major, or they isolated two major, radioactive components, which were majorly polonium and radium. So they got polonium. I hope I'm talking. And they also got radium. These two substances were observed to be highly radioactive. Now we've said that
Yes, sir.
radioactive materials, okay, radioactive materials, most importantly atoms. Now these substances are affected by what's it called, pressure. Neither are they affected by temperature, and so they occur spontaneously. So I've told you what spontaneously means. That means something that occurs on its own without any external effect. There is a major difference between radioactive substances in principle. So normally when you look at radioactive substances, they undergoes radiation or radioactivity, meaning there is a spontaneous emission. There is what? Spontaneous emission of radiation. Are we listening? Now, and it is also not affected. It is not affected by temperature, non-pressure. So unlike the other types of reaction, like normal chemical reactions, which I'm going to talk about, some differences between radioactivity and chemical reaction, or nuclear reaction and what chemical reaction. So apart from that, radioactive materials are not affected by these factors I've talked about, or they are not influenced by the following factors: temperature, pressure. Neither are they affected by light, but they can affect a photographic plate, so they can make it visible. So they can cause fluorescence. So let me start by this. They can cause what? Fluorescence. What is the meaning of fluorescence? Anybody? What's the meaning of fluorescence? It means they can glow. So they can glow. So they can make material to glow. So that's the meaning of fluorescence. Materials like zinc sulfide and possibly anthracene. So this material will glow when they, yeah. So they have ionizing effect and penetrating power. I'll explain what that means. Ionizing effect and penetrating power. Now, unlike the normal chemical reactions, because in chemical reactions the nucleus is not involved, but in nuclear reaction, from the word itself, nuclear, so the nucleus is actually involved, and it is the nucleus that is disintegrated. For example, when you have an atom, you are going to see the nucleus is in here, and then the electron is here. So in nuclear reactions or radioactivity, as the case may be, it is this nucleus that is always affected. Are we together? So when the nucleus is affected, we are talking about nuclear reaction. Are we there? Or we call it what? Radioactivity. Does that make sense?
Yes, sir.
But when electrons is actually involved in the process and the nucleus is not affected, that one is dealing with chemical reactions. Is that okay? Now, in chemical reactions, for example, there are a number of factors that can affect the chemical reactions, like temperature. Temperature will affect a chemical reaction, right? Concentration will affect a chemical reaction, right? Are we together? Pressure will affect a chemical reaction, right? Surface area, and so on and so forth. Those ones will affect a chemical reaction. But they don't affect what? They do not affect a nuclear reaction. So that's why we said they are not affected by temperature nor pressure, right? Now, during the process of radioactivity, most importantly radioactive decay, there are three major types of radiation that are emitted. So, radiation emitted, radiation emitted during what? During radioactive decay. So, what are the radiations that are emitted during radioactive decay? Number one, we talk about the alpha particles. Are we there? Am I talking?
Yes,
So,
sir.
these alpha particles are
Yes, sir.
represented by this alpha. We have number two, the beta particles. The beta particles are represented by this. Right, this one. Okay, number three, we have the gamma ray. The gamma ray is represented by this, right? That is the alpha particle. So the alpha particle is represented by particle. So that is represented by, well, helium particle. So how do you represent helium particle? So, hello?
Is represented by helium.
Yes, helium.
H.
He, 2 atomic number and 4 mass number. Number 2, the alpha particle is positively charged. It is positively charged. Are we together? Number
Yes, sir.
3, it is a heavy particle. It is heavy. Number 4 is that because it is heavy, it will not be able to move fast. Anything that is heavy will not be able to move fast. So it has a low penetrating power. Are you listening?
Yes, sir.
So the penetrating power of alpha particle is very low. It does not penetrate very well. So because it is heavy. So it can be stopped. It can be stopped by an aluminium sheet of about 0.1 millimeter thick. Are we there? To show
Yes, sir.
how the penetrating power of alpha particle is low. So in fact, it can even be stopped by paper. So if that paper is a little thick, so it's going to stop it. Now, it is having a very low penetrating power, but high ionization energy. So the ionization energy of alpha particle is very high. Let's take a scenario of somebody that is very fat, and the person wants to run a race. Definitely the person will not run very fast. So it means the penetrating power of that person is low. Am I communicating? But because the person is fat, we are assuming that person is alpha particle, and the person is to pass through a wall. you know because the person is big, let's assume that the person is passing through that wall. So the amount of bricks, the amount of particles that will be removed as the person is passing through the wall will be more than 18%, isn't it? Do you understand that illustration? You get the point. So the alpha particle has low penetrating power, but what, high ionizing effect. You get it?
Yes, sir.
Then another thing to note under the alpha particle is that the alpha particle can lead to what we call fluorescence. It causes fluorescence. What did I say fluorescence is?
Glow.
Glow.
Yes. So it causes some materials to glow. So it causes fluorescence on materials like zinc sulfide. So if you're having a zinc sulfide screen, for example, let's assume this one is zinc sulfide, right? And then you have alpha particle shining on it. So this alpha particle that is shining on it is going to make this material to glow. So so this thing will now start shining like this. It will be shining. So that means it is causing what? Glow. It is glowing. So that's what we call fluorescence. So alpha particle can cause zinc sulfide to fluorescence. You get the point? Is that okay?
Yes, sir.
Now
Yes,
that's
sir.
the first material. Note that I said that the alpha particle is a heavy particle because I'm going to tell you the implication later. Now the next one after the alpha particle is the what? Who can tell me the next particle?
Beta particle.
The beta particle. Now as for the beta particle, the following are to be observed. Number one is that the beta particle is what? Is represented by electron. Represented by what? E minus 1 0. So that's how to represent the beta particle. Is that okay? So, and it is negatively charged. It is negatively charged and it is light. Right? Are we there? So if something is light, definitely it is going to move very fast. So the penetrating power will be very, very high. So that means the beta particle has higher penetrating power than the alpha particle. You get that? Am I talking?
Yes, sir.
Yes, sir.
So higher penetrating power than the what? Than the alpha particle. So the reverse will be that it's going to have a lower ionizing effect than the what? Beta particle, because it is not as big as the beta particle. So the ionizing effect will be lower. So we say it has what? Lower ionizing effect when compared to what? To the alpha particle. Does that make sense? Can I proceed?
Yes,
Yes, sir.
sir.
So yeah, it can also be stopped by aluminium of a higher thickness since it has more penetrating power. So it can be stopped by aluminium of a thickness of about 5 millimeters thickness. Are we together? So can be stopped by aluminium of about 5 millimeter thickness. Is that clear? Or on anthracene. Anthracene, not zinc sulfide. So what does that imply? So it can only make anthracene to fluorescence. It cannot make zinc sulfide to fluorescence. Unlike the alpha particle that make the zinc sulfide to fluorescence, the beta particle do not make zinc sulfide to fluorescence. Rather, it makes anthracene to fluorescence. Is that clear?
Yes, sir. Yes,
Then
sir.
we have the gamma ray. So the gamma ray has no charge. It is neither positive nor negative, right? So it's very similar to the X-ray and the light, the visible light ray. Similar to the X-ray and what? Visible light ray. It has the highest ionizing effect. I think that's okay. The highest penetrating power. It has the highest penetrating power between the three now, but lowest ionizing effect. You have the lowest what ionizing effect. Does that make sense? You said it causes what fluorescence, just like others, right? Fluorescence is the ability of a material to glow, so it also causes fluorescence. It can cause fluorescence in zinc sulfide, right, and even in anthracene. So that should be noted. Okay. Now, if you're having a particle here, and that particle was made to emit radiations, and then you have a magnetic field here. Now, if this is positive and this is negative, are you paying attention? There will be a possible radiation that will go straight this way. No deflection. That means it's not moving to the positive end, neither is it moving to the negative end. So this is considered the gamma ray. It has no charge, right? Now there will be a particle that will deflect this way, right? This particle that is deflecting this way is deflecting slightly, and that's going to be positive. Since it is moving through the negative, that will be a positive particle. And the positive particle is what? Alpha particle, right? So deflection here is going to be light. I hope you are listening. The reason why we have light deflection is because the alpha particle is a heavy particle. Now, also going to have a particle this way. Now, this deflection is going to be done lightly. Sorry, strongly, because it is a light particle. You know, if you are to pull a boy of 2 years old and you are to pull a boy of 10 years old, the boy of 2 years old, you pull that boy more because the boy is not heavy. That's exactly what is happening. So the beta particle is a light particle. So the deflection is going to be done strongly because it is a light particle. So that positive end will pull it very well. And so this particle is negatively charged because it is deflecting towards the positive pole. And so which particle is negatively charged? That's the what? Beta particle. And so that's going to be represented by this -1, 0. So that's our beta particle. Now we can also have another illustration this way because it might be tested on stuff like this. So you are going to have one is this way, another one this way, another one this way. So if this is stopping at this end, and another one is stopping at this end, and another one is stopping at this end. So who can tell me what this first one A would be, B would be, and C would be with your reasons? Anybody?
A is the alpha particle
A is equal to
because
alpha
it
particle.
has
Why?
because it has the lowest penetrating power.
Because it has the lowest penetrating power. Is she correct?
Always beta
Is what?
particle. Beta particle.
Yes, the beta particles. Okay, also represented as E -1, 0. So then followed by what? The gamma ray.
Gamma.
Good. So when you have to represent them based on their increasing penetrating power. So alpha particle is less than what? Beta particle. And this is less than what? Gamma ray. So it increases this way. You say increasing penetrating power. Is that okay?
Yes, sir.
Now, tools or instruments for detecting radiation. So what are the tools we use in detecting radiation? Number one, we have the photographic plate. You know, that was what, what's his name? Henry Becquerel actually used. That was what he discovered. That led to the discovery of radioactivity, photographic plates. Is that okay? Number two,
Yes, sir.
you have the zinc sulfide screen. You know, we always use that screen also for detecting it. Because by the time any radioactive substance comes on it, it's going to make it shine. Right? That means it's going to fluorescence, it's going to glow. Zinc sulfide screen. Are we together?
Yes, sir.
Number three, you have what we call the Gigamolar counter. The Gigamolar counter. Okay. So we have the scintillating machine, or sometimes they call it scintillating counter, scintillation counter, as the case may be. Let me. Okay, we have number four, scintillation machine. Number five,
Yes, sir.
we have the diffusion cloud chamber. Diffusion cloud chamber. So these are the few instruments that you're supposed to be aware of that are actually used in detecting radiation.